All right, members of AP Calculus, we're here for a video to talk about the fundamental theorem of calculus. And in order to get to this fundamental theorem of calculus, I want to talk with you about just one simple question to start off with. All right, so hypothetical situation, we've got Bonnie and Clyde who just robbed the Mansfield Bank, and so here in West Bridgewater. So they are now at West Bridgewater International Airport. They're looking to get away. They decide they're going to split up in order to make it harder for the police to catch them. And they're going to rendezvous down in Fall River. All right, so one of them hops into a getaway car and the other one hops into a getaway plane. And they're going from point A to point B. All right, so point A is the West Bridgewater International Airport, and point B is the Fall River International Airport. And we want to know how far is it from point A to point B. Okay, so they're both traveling, and what's going to happen is, let's see, let's put Clyde in the car. Clyde is going to take Route 106 over to 24, shoot down Route 24 all the way to the Fall River Airport. And meanwhile, Bonnie's going to fly. So when she takes off from the airport, she actually flies over Route 106 and then down Route 24. So she's basically flying the same path that Clyde's taking in the car. It's just she's up in the air, so that way she knows she can just use the landmarks of Route 24 as her guide so she doesn't get lost up there. Okay, so that's the plan. They're covering this exact same distance. Well, how far did they travel? All right, well, if Clyde's in the car, we can tell how far Clyde traveled. He just needs to look at one item, right? The car's odometer. He needs to look at the odometer at the start of the trip and the odometer at the end of the trip. All right, so if he knows his position at the start of the trip and he knows his position at the end of the trip, then he can do some quick math and come up with how far it is from one airport to the next, correct? Let's say at the start of the trip, the odometer says 100,000 miles. And at the end of Clyde's trip, it says 100,036 miles, okay? Well, we know that 100,036 minus 100,000 means that it's a 36-mile trip. So if we're figuring out how far it is from point A to point B, using the car, all right, we would look at the position of the car at the end of the trip. Remember, S is our function for position, all right? So position of the car at the end of the trip, that's B, minus the position of the car at the start of the trip. Okay, so 100,036 miles on the odometer minus 100,000 miles on the odometer at the start of the trip tells us that Clyde traveled 36 miles by car in this getaway route. Okay, so that's how we can figure out how far Clyde traveled. Now think about this from Bonnie's perspective for a second. Remember, the planes don't have odometers, okay, because it's all about being up in the air, obviously, okay? But we've already talked about this in class about how we can cover distance traveled when we don't have the position, but in fact have the velocity function. All right, remember we talked about looking at the velocity, and that led us to Riemann sums, but we now know that a definite integral would be the equivalent of checking the velocity of the plane the entire trip, for however long that it is. The definite integral just says check it a million, a billion, an infinite number of times. But if we want to know how far that Bonnie traveled, we wouldn't be dealing with position, we would be dealing with the integral, again, from A to B of the velocity function. Okay, and that tells us how far it is from point A to point B in terms of the plane ride. Okay, now remember, the plane was flying directly over the car. So if this tells us the distance traveled by the car, and this tells us the distance traveled by the plane, and it's the exact same distance, that means that we can set these two equal to each other. All right, so we have S of B minus S of A is equal to the integral from A to B of the velocity function, v of t dt. Okay, these two both represent the distance from one airport to the next. All right, now this is pretty key here. Let's finagle this equation around a little bit. We see velocity. Velocity is what's the connection between velocity and position? Exactly. Velocity is the derivative of position. So let me write this again. And I'm going to write it as S prime of t dt instead of velocity. So we've got S prime. Okay, now, this is S, and this is S prime. That's position. Let's just make this more general instead of position. Let's turn it into a function. Okay, any general function. All right, so let's use F. So we've got F of B minus F of A. And then we have the integral from A to B of F prime. All right, and then I'm going to switch from time to X, because X is our general independent variable. So instead of S of t prime of t dt, we have F prime of x dx. Wow, look at this. This is our fundamental theorem of calculus. Okay, and this is relying on the fact that if f is continuous on the interval from, continuous on the interval from A to B. All right, right here, this is known as the fundamental theorem of calculus. And you're saying, okay, well, what's so important about this? Well, let's look at what we see on the left side. On the left side, we see a function, right? F. Okay, it's f evaluated at b and f evaluated at a, but it's just the function f. We'll take a look over on the right side. What do we have? We don't have f. We have f prime. But we also have the integral. Well, we have two things happening here, derivative and integral. And over here we have neither. What does that mean? That means that the derivative and the integral wiped each other out. Okay, we took a derivative, we took the integral of the derivative, and that brought us to the original function. So the derivative and the integral are inverse operations in essence, okay, like addition and subtraction, multiplication and division, square rooting and exponents, logarithms and exponential functions, derivatives and integrals. They are inverse operations. They are the opposites of each other, if you will. Okay, and that means that they wipe each other out, and what we're left with is just the function evaluated at b minus the function evaluated at a. It connects this whole first half of the course that we did on the derivative with this second half of the course that we're working on right now. That's our fundamental theorem of calculus. That's what makes it so important. It's telling us that the derivative and the integral are in fact connected. Okay? Now, we're going to look at more videos regarding this in the future, but this is where our fundamental theorem of calculus, everything builds off of it.